Output devices are things that allow the PLC to do something in the real world, not just calculate what should be done, but to actually activate something. So these are typically actuator type things. There are several symbols for the subset of actuators that are control devices, because control devices are things that have to do with control of the system, kind of like switches, but going a little bit farther toward where they're doing a little bit more. So you have indicating lights, for example, like a pilot light. You can see the standard symbol there. There are control relays, which may or may not actually activate something in the real world. It may just be a relay that's used for control, or even relays that are larger that are intended for starting motors. A motor starter, for example, even a, so there's a motor starter coil. There's a motor overload relay contact symbol, and there are other symbols obviously that go with the motor starter switches and the overload sensors and so forth. But these are all output type devices. Now, what's kind of interesting about this is that a lot of them are paired. For example, the pilot light isn't paired with anything, right? A pilot light's pretty simple. You apply the correct voltage across it, and current flows through it, and the light comes on. With the control relay doesn't just have a coil. The coil itself is the output device, but there are other parts to that coil, the relay part, the switch part, that is really part of that device. So this lower motor starter coil, I would rather see the three switches that are associated with supplying power to the motor, which is typically going to be a three-phase motor, rather than just the overload switch. But the overload switch is a valid part because often the contactor and the overload are connected together and form a whole motor starter. So that's all right. There are many other devices, alarms, for example, heaters. There are heating elements even in your electric water heater, if that's the type you have, and this would be the standard symbol for it. Now, obviously, there are bigger heaters available in industry. Some heaters are electric, some are gas, but gas heaters are typically a little bit different, because if you think about what we're doing here, we're really talking about electrical wires and things that are connected electrically. So if you have a gas heater, you probably won't have an electrical device going to that heater. Yeah, maybe to spark it and get it going, but that's an ignition circuit. Rather, what you would have is something like a solenoid valve that is used to turn on or off the flow of gas. Now, solenoids themselves are useful, and you can see the standard symbol for a solenoid there. Solenoid valves are so called because they have a solenoid that moves a stem, basically a valve stem, within the valve body. And most often these are on-off type valves, but you can get valves that are proportional as well. In our class, though, we're focusing on on-off types of controls. So the types of solenoid valves we'll deal with are not proportional valves, they are on-off type valves, and this is the standard symbol for it. You'll notice that the wire goes through the coil, the upper part that's labeled SV. That lower bow tie looking thing represents the valve itself and would have pipe going through it in a diagram. A standard symbol of a motor is pretty simple, just a circle with MTR in it, and then you can see an alarm horn or whatever type of horn this may be. It may not be for an alarm, it may just be a warning horn, but you can see the various symbols there. So an actuator device is a device that changes the electrical signal into mechanical movement. And there's many different types here. The simplest to think about is the electromagnetic solenoid, where all you're really doing is running current through a coil, and that makes a plunger move, and so that causes mechanical motion. It can apply force and move something in the real world. There are small things. An actuator could be a piezoelectric element that only moves a very small amount. That is possible too. It wouldn't be common in industry, whereas a solenoid would be relatively common. But there are many different types of actuators. Solenoid valves I've already mentioned a little bit, but here's a nice cross section where you can see the solenoid mounted on top, and the plunger that's actually moved is the valve stem, as I said, so that the valve can be seated or unseated and allow flow or block flow. Now we'll focus not on the fluid side but on the electrical side. So you can see on the left hand side an L1, L2 of power rails where power tries to flow through, And when the solenoid coil is de-energized, when power is not flowing through it, then the valve is in one state, either passing fluid or not passing fluid. And you can buy them either way. You can buy valves that are normally open or normally closed. And then on the right hand side you can see where current is actually applied. There's a switch closed somewhere that allows current to flow through the solenoid, which is that right hand symbol in red, and the plunger then goes in and blocks flow, the fluid flow. Now, one interesting thing about this, you'll notice both of these have springs, so most often these are spring return type mechanisms. So not only does the coil have to move the spool, but it also has to work against the spring and apply force against the spring. So most often these types of valves are, you have to apply current to them continuously for them to stay in the open or the closed situation, whichever configuration is the non-default. And you can buy these valves in either normally passing fluid or normally not. They unfortunately also use the terminology that switches use, so it can be confusing. But anyway, there's a solenoid valve. There are other kinds of valves. In my home heating system, I bought some valves that they're not really solenoid valves, but they are electromechanical valves. The way they work is they've got a little motor, and that motor has a gearbox on it, and when you apply power, the motor actually turns the gears, and I don't know if it closes or opens the valve. It doesn't really matter. It changes the state to the one. But when you remove power, it's kind of interesting because all the time that power is applied, the valve charges some supercapacitors, so that when you remove power, it's able to change state, and it has enough power then that's stored up to change the valve's position. That way you don't actually have to have power to the valve continuously to hold it in one position or the other. So one of the disadvantages of the classic typical solenoid valve, or solenoid valve, I don't know how you say it properly, but a big disadvantage of these is that you do have to apply power continuously in order to reach one state. So they can overheat. They're going to generate heat because all the energy going into the coil has to come out as thermal energy, since there's no work being done, no motion. Stepper motors are a fairly common type of motor in industry. They're different than a regular motor in that you don't just apply power to it and it just turns continuously. You have to instead apply power to different coils inside of the motor in the right sequence for it to step to the next position. So you apply power to one coil, the motor steps to that position. You apply power to the next, the motor steps to that position, and it just holds that position as long as you apply power. So it can have a fairly high holding torque because that's really what it's doing. It's just moving to a position. It's kind of like a solenoid valve, kind of like a solenoid with multiple positions, except it accomplishes those multiple positions by multiple coils. But when you think of a stepper motor, don't think of a regular motor where you just apply power and it turns continuously. They're more complicated than that. But there are some advantages to these. One is the relatively high holding torque. Another is the fact that you can, if you've sent a command to step, 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 you know where the stepper motor is. You don't need feedback from it, because as long as the torque requirements of the motor are not, or the torque in the system doesn't overcome the torque available from the motor, then the motor will do the steps and it'll be in the position you commanded it to be in. Sometimes stepper motors are used with position feedback to make sure they've reached the intended position, but often they're used without. And so, now, disadvantage of this motor, well, it's basically like a solenoid in that to hold a position, you keep applying current to the particular coil that the motor is supposed to hold position at. And the problem with that is all that electricity and all that power goes into heat. It has energy is conserved. So if electricity and power therefore go into the motor, then it must change into some other form, and it changes into thermal energy, or what you probably call heat. So the speed is just proportional to the number of pulses. So you give it pulses basically to move it from one set of coils to the next, and the speed just depends. Now you can send pulses too fast so that the motor mechanically can't follow the speed that's desired. So there can be over torque situations where the motor can't provide the torque you're asking it to because the machine's just too heavy, if you will, the load's just too high. Or you can have inertial effects where you've applied too many pulses too fast and the motor simply can't accelerate that quickly. And it turns out that the faster these motors turn, the lower torque output they can have too. So that's another potential problem. Servo motors are a little bit different. A servo motor might look a lot like a stepper motor, but you'll see that they look different. The way they usually operate, I don't want to say these are always DC motors, but they are frequently DC motors. A servo motor has some type of feedback, some type of, whether it's an encoder mounted on the back of the motor shaft or some other type of feedback. That feedback is used for determining the position of the motor shaft, and that way you can apply more power to the motor or less to try to get it to the position that's desired. So they're not stepper motors, but you can do some really good control with these if you have good feedback to get the motor to particular positions. In one of the other courses I teach, I show students how to take a DC motor and move it a certain number of steps, if you will, from an encoder on the back side of it and hold a particular position. It's just a DC motor. So there's a lot of interesting things you can do with this. The feedback device does not have to be an encoder. Encoders do sense position. Tachometers sense speed, for example. You can use an encoder to calculate speed. You can use a tachometer to infer position. Those are basically integral derivatives of each other, and all that has to be done software. So it's pretty common with a servo motor to have a fairly complicated control system. You can see one pictured there along with the servo motor that's used for either positioning or whatever the case may be. It's more precise control than just pull the trigger on my battery powered drill and the motor starts spinning. No, servo motors are much more precise and much more controllable because of the feedback loop that they naturally provide. So these are useful for all sorts of things, but primarily positioning. And servo motors sort of compete with stepper motors. And one of the nice things about servo motors is that if you have the right controls, they can often outperform a stepper motor for many applications. And they're also usually less expensive, there's less power draw, there's a lot of good advantages, but it comes at the cost of being quite a bit more complicated than stepper motors.